Assignment 22, this is 3.8, sinusoidal equations. Your essential question: how do you find rates of change of sinusoidal functions in real-world problems? All right, so let's review sinusoidal equations. So here's a sinusoidal. This we did in pre-calculus, where you basically had an equation that took the form of y, or f of x, equals some a times cosine of b times some x minus d plus c. So hopefully this is looking familiar to you. And we'll just recall several of these parts. So first of all, starting with c. C is your vertical shift. So another way that we've referenced this before is maybe the midline. And your book has all of this actually written out on page 110, and they call it the vertical translation. Okay. Vertical shift, vertical translation, same thing. All right. All right, so your D, hopefully this looks familiar. Your D then is your horizontal shift, or your horizontal translation. Your B, let's see, I'll put that over here. No, I'll put it here. Your B is basically, it's the relationship, I should say, B equals 2 pi over your period. Okay? Period. And A, well, that's your amplitude. And your amplitude is your distance from that midline. Okay, so you'll have a high point, you'll have a low point, and those will each have a certain distance from that midline. So they call it like a vertical dilation. Okay, your amplitude basically gives you your vertical dilation. Or you can think of it as the distance that your high or low points are from the midline. Okay, so hopefully this is all ringing a bell and you recall doing these last year. And we're going to actually work a problem together on it. So I gave you this handout in class. And this has a really great thing that can be modeled using sine or cosine, so hence the sinusoidal equations. So suppose that the water wheel shown in this figure rotates at 6 revolutions per minute. You start your stopwatch. 2 seconds later, point P, which is on the rim of the wheel, is at its greatest height. Okay, so let's think about this diagram a little bit. So first of all, what is the greatest height that they're going to have above ground? So the greatest height above ground, let's see, if I had this 6 feet plus 7 feet, then that tells me that my highest point above ground is going to be 13 feet, right? So at my highest point, I'm going to be at 13 feet. And that just so happens to happen at 2 seconds after I start. So when time equals 2, I know that I'm at my highest point, which is 13 feet above the water. Okay. So I think the first thing that we should do is we should, oh, well, here's a problem. My time is 2 seconds, so this is seconds. My revolutions are given to me 6 revolutions per minute. So actually, probably the first thing that I should do is I should convert from 6 revolutions per minute and see how many that is per second. So if I have 6 revs per minute, and I know that there are 1 minute will give me 60 seconds, then that tells me that I'm going to have 6 revs per 60 seconds. And I can do this a couple ways, but how about 1 revolution per 10 seconds? So every 10 seconds I get 1 revolution. Okay? Alright, so I think that the best thing that I can do here is to get an understanding of what's happening here mathematically, and that might be to actually draw this out. So they want us to model the distance d of a point P from the surface of the water in terms of the number of seconds t the stopwatch reads. So that's telling me that my input here is seconds, okay, and my distance from the surface of the water is my output. So I'm actually going to draw myself a little graph here, because before I can come up with a model for this, I need to visually see what's happening. And this thing actually goes underwater, right? So my distance might actually go below water a little, so I'm going to go a little bit negative. That's a little bit better. Where this is going to be time in seconds, and my d is going to be in feet. Let's see, where did I see that? Model the distance from the surface of the water in terms, okay, so feet from surface. All right. Well, let's see. The first thing that I know is that at 2 seconds, I'm at my highest. Okay, so at 2 seconds, I'm at my highest feet, which is 13. So when will I get back up to my highest height? Well, that's going to happen after a whole nother revolution. And that's going to happen in 10 more seconds. So in 10 more seconds, so at 12 seconds, I'll be back up to 13 feet. And of course, I didn't leave myself enough room. All right, so at 12 seconds, I'm back up to my highest height of 13 feet. All right. So let's go back to that. So 1 revolution per 10 seconds. Notice how I would have completed an entire period. If I started up here and I went all the way back around, that's an entire period. So this right here is actually my period. Next, let's figure out where my lowest point is. So if it takes 10 seconds to go all the way around, then halfway through that would be 5 seconds, right? And that's going to take me to my lowest point. So 5 seconds from 2 seconds will bring me to 7 seconds. And my lowest point, let's look at this water wheel. So the water wheel goes up 7 feet from this mid area, basically the center of the circle. Okay? And then it's going to come all the way back down around. The problem is, from the water to the middle here is only 6 feet. So that means that the water wheel is going to go 1 foot underwater, or 1 foot, right? So right here I'm going to have 1 foot. So that tells me that at 7 seconds, this thing's going to go down to -1 feet. So now I can figure out where my midline is. My midline, think of my midline as like my midpoint, okay? So I'm looking for where is it, or right now I'm actually answering what's my amplitude, right? So if I can figure out what that midline is, then I would know my amplitude. So where is it? Where should this midline be drawn so that I am equidistant to my highest point and to my lowest point from that midline? Well, one way to do this is to actually just go ahead and calculate your midpoint. So I'll do m equals my highest, which is 13, plus my lowest, which is -1. Divide that by 2, right? I just take the average of the biggest and the smallest. So that's going to give me 6. So my midline should be at 6. Oh, this is not good. 1, 2, 3, 4, 5. Let's pretend like it's there. So I have a pretty rough graph here. I'm going to go ahead and say that, before 2 seconds, it was somewhere lower. Once I come up with the equation, I'll know all the specifics. I need to go down here somewhere. I need to end up probably somewhere between around 4.5 seconds at my midline. Come down. Right, it's sinusoidal, so we know that it looks like either the cosine or the sine graph. And something like this. So keep on going. Okay, so there's a nice graph. So now let's actually come up with a model. So let's remember that our model for this, let's see, I'll write it up here. We can do our distance is going to be, well, some a, we'll use cosine. This looks to me like a cosine graph, or it looks easiest to get it to be a cosine graph because I can just shift it over here, right? So basically it's been shifted to the right 2. Originally, if it was a cosine graph, your highest point would be on your y-axis. This has just been shifted to the right 2. Okay, so cosine b x minus d plus c. And I just want to point out, I didn't do this earlier, when I look at this equation in your book, they put c in the front. I chose to put it at the end. It really doesn't matter. I put it in the end because we're used to looking at functions like x minus h plus k. So imagine your d and your c are like your h and your k. Okay, but it can also go in the front. And so coming back to this now, I'm looking at this equation, and our input is actually time, so t, so it should not be x, it should be t. Okay, so let's get some pieces of this. Okay, first of all, why don't we start with our period? So our period, we get 1 revolution every 10 seconds. So our period is every 10 seconds, we get a new period, right? Okay, so b, looking at this, is equal to 2 pi divided by our period. So b is equal to 2 pi divided by our period, which is 10 seconds. So basically we get pi over 5 as our period. Okay, so that's going to be important. let's see, we've got, as we had talked about, if this was a cosine graph, well, the cosine, the highest point is always on the y-axis. And at this point, my highest point is shifted 2 to the right. Okay, so my D has a horizontal shift of 2. My midline, which we already found, was at 6. Okay, so there's my midline. So let's think about our amplitude. So my amplitude, basically ask yourself, how far from 6 do I need to go up or down to get to my max or my min? And that would be 7. Okay, and if you think about your cosine graph, originally your cosine graph has a midline at the horizontal axis. So it actually has it at the x-axis or the t-axis. Problem was that this midline or this entire graph has been shifted up 6. So that tells me that I have a c that is equal to 6. Okay, so I think that gives us our final function. I think we have every single piece that we need here. So I'm going to write this a function, my distance as a function of time is equal to my amplitude, which is 7, times the cosine of my b, which happened to be pi over 5, times, and then that's going to be t minus my d, which was 2, plus my c, and my c I was shifted up 6. Now this can get a little bit tricky when you're punching things into your calculator. So you have to understand that what you're plugging into your cosine function is actually this whole piece right here. Okay, so that can get a little bit tricky. So it might help to have those brackets there. All right, so now we need to figure out, well, what's the equation for the derivative, or d prime? Okay, so I'm going to write that as d prime of t. I'm going to leave my coefficient there. Now I'm going to take the derivative of cosine. The derivative of cosine is negative sine. So I'm actually going to have times negative sine. I'm going to keep my inside function here. Okay, so I'm keeping the inside function. I'm using the chain rule here. Let's put these brackets there. Okay, but now that needs to get multiplied by the derivative of the inside function. Okay, so let's think about this. If I had distributed this pi over 5, that would be pi over 5t minus pi over 5 times negative 2, whatever that is. That's a constant. So really I only care about the pi over 5t. And so that means that I'm going to end up multiplying this by the derivative of pi over 5t, which is pi over 5. Okay, so I've taken care of this entire inside function now. And now I'm going to go back to this and say, okay, plus, well, derivative of a constant is just 0. So I'm pretty much done here. Okay, so it might be more helpful if I wrote this a little bit neater. I'll do negative 7 pi over 5 sine of this inside piece. Okay, so this is my answer for B. This was my answer for A. This graph just helped us. That's all it did. Okay, so how fast is the point on the water wheel moving vertically when time equals 5? So we care about the rate of change. We care about the speed, okay? And that would be feet per second, right? So we care about the rate of change that's happening, right? So we care about like a tangent line that's been drawn to this, which would give me the slope of anything on here, okay? Or the slope of any tangent line on here. All right, so that means I'm going to plug these into my derivative function. So d prime of 5. So I think I'm actually going to pull out my calculator for this. And I'm going to plug in my original function. And then I'm also going to do the numerical derivative of that. So let's see what I get here. So I'll do 7 cosine pi divided by 5 and t minus 2 or x minus 2. And then all of that I'm going to add 6 to. Then I'll go down here and I'll do my numerical derivative. So I'll go to math 8. And I'm going to do that with respect to x. And here I'm going to do my y bars, y bars, and I'm going to use my first function. And I'm going to let x equal x because I want the whole function. Okay, let's see now if I can get this to come up in my table. So my window, I'm going to start, I can start at 5, go up by 1. Alright, so my derivative here is negative 4.183. So I can come back to this and I can just say, well, d prime of 5, or if I had plugged it into here, will be negative 4.183. And now this will be really easy to figure out the derivative when t equals 9. I just need to look down here. Looks like it's going to be 4.183. Alright, so D. Let's get rid of this real quick. At t equals 5, is the wheel moving toward the water or away from the water? Justify your answer. Okay, so at t equals 5, right? And let's remember that this is my distance from the surface. So at t equals 5, I'm getting a negative slope. That means that my original function has a downward sloping tangent line. Okay, which basically tells me that I am heading towards the water. So at t equals 5, the wheel is moving toward the water. And we can think of this as, our rate of change of our displacement function. So this is our displacement function, and we're taking a rate of change of that. And so that tells me that that's my velocity. Okay, so the velocity is negative. Its distance from the water is decreasing by basically 4.183 feet per second. So that's a pretty solid answer. Okay, at t equals 9, is the wheel moving toward the water or away from the water? Justify your answer. Okay, so let's look back at this. So my derivative is positive. So that should tell you that my function, I get a positive slope of a tangent line at time being 9 seconds. That tells me that I am moving away from the water. My velocity is positive. Okay? I'll answer that one over here. So at t equals 9 seconds, the wheel is moving away from the water. At 4.183 feet per second. And we can say velocity is positive. Okay, let's just think of one more thing here. So what I'd like to talk about now is, where do we have the fastest velocity? Where are we moving the fastest? So we can do this a couple ways. We can look at our graphs and we can say, where's our fastest or our steepest slope? Which would tell us our fastest velocity. Okay, so maybe you have an idea there. So basically taking your ruler and saying, well, how's my slope looking here? How's my slope looking up here? How's my slope looking here? Right? So just trying to think, hey, where's my fastest rate of change? Another thing we can do is we can look at our derivatives. Oops, except for that mine turned off. And we can say, where are my fastest velocities? So let me go in the positive direction. So at 7, velocity is 0. Okay. But as I move further and further, I notice that, okay, starts off at 2.5 feet per second. Then I'm at 4.183 feet per second. And I can go over and get maybe a little more accurate. So 4.18296. There's not much difference there. They're not going to show me any difference. Okay, and then I'm slowing down again, right? So after 9 or 10 seconds, I'm now going at a slower pace. Might actually help if I did, if I changed my window here. Maybe I can go by 0.1 and I can start at, because we were looking at 9. So why don't I look at 9 here? So at 9, I'm at 4.183, 9.1, I'm at 4.26, 4. Looks like I'm getting a little bit faster, 896, let's go down a little bit. So about 9.6 seconds is probably where I'm going my fastest, right? The fastest rate of change, okay? And then at 9.7, starting to slow down again, starting to slow down. Okay, so that's really, if I think about it on my graph, that's really at this kind of where I'm meeting the midline here. And that appears to me on my graph, that looks like that would be where you would have your fastest rate of change. Okay, so just an idea of thinking about, hey, where is it increasing or decreasing the fastest? And before I leave you, I'd like to just come back to what we originally set up here. And a couple of things that maybe you caught or maybe you didn't. But, when we were finding that midline, remember we found the average of the highest and the lowest points? So that's a really good way, if you were having a hard time, you could basically just figure out, take your max, add your min, divide by 2. Okay, it's basically the average. All right, and then sometimes, you may have a hard time finding that amplitude. Okay, and so one way that you can find your amplitude, it's a little bit more, like this is average. This is really intuitive, okay? But basically what you're looking for is distance, right? And when we're looking for distance, we're going to do the max minus the min divided by 2. And that will give you where your amplitude is located. Okay? All right, so a couple more things I just want to add. What is a sinusoid graph? And why do we care about them? So a sinusoid graph is going to be a graph of either sine or cosine. They're interchangeable. Because if you remember from last year, Sometimes you'd come up with a sine graph if you shifted it one way, but if you shifted it a different way, it was a cosine graph. And as long as you put all the pieces together the correct way, either one can count. They occur in connection with periodic that's not how you spell with. Motion. So things that, happen in those periods. So, for example, a tide, sunset or sunrise, sound waves, and so much more. But we'll just leave it at that.